simulation modeling using this. This topic is a bit this is a bit more technical because the problem is also much bigger than what we were doing for monitoring the crop residue burning. Anyway, so we will talk basically in this lecture the need for yield mapping and prediction. What are the approaches for yield modeling using satellite images, using historical yields, in-season yields? And then we will also talk of operational system where convergence of evidence takes place. And that is where it is not that it is the operational system to which we are trying to go for. So as you know that why remote sensing should be used for crop yield modeling. The important thing is because it is again, this data is available from a range of spatial and spectral resolution. So if you are interested in field scale yield modeling to a regional scale yield modeling like district or state, the corresponding spatial data, their temporal resolution, spectral resolutions are available. And of course, you know that crop yield always is a sum total of whatever growth happened over a period of time during the crop season. So many times the yield modeling, you need to do repetitive monitoring to finally arrive at the final yield figures. So remote sensing that way is also amenable because satellite, they come at a constant interval, right from every day to 5 days to 15 days. And nowadays, many private companies have come up which are providing a very high resolution spatial spectral data, as well as at a very high temporal resolution. So every day kind of at a 3 to 5 meters, you can get the data in case you need that, in case your application has that kind of requirement. And we had seen that remote sensing actually very clearly observe the crop vigor, which has a very sound scientific basis also. And not only crop vigor, but it also remote sensing can be used to observe crop environment like rainfall, soil temperature, soil moisture, temperature. So which are all the determinants of crop yield. And of course, remote sensing is digital in nature, whatever we are doing nowadays. So it is amenable to computer algorithms. The methodologies are objective, they can be easily shared, stored, and of course, the cost per unit area is lowest as compared to any other method you do, whether you do aerial surveys or you do manual surveys. So the cost is lower. And another important thing is that now satellite data, we have multiple sources from multiple national space agencies to commercial private sector. And many of them are providing standardized historical data sets. So in case you want to develop empirical yield models, you need to have historical data sets where you can use any of either statistical model or machine learning models. So standardized data sets are also available. Now, what is the problem of using remote sensing for crop yield modeling is that remote sensing does not measure the crop yield directly. Like in field, we go, we harvest, and we take out the economic yield part and then wait. But remote sensing is not doing that. It does not directly measure the crop yield. And another problem is the deriving crop information when it is in early growth stages. That is, when the crop is having a lower leaf area index, then it is difficult to measure the parameters of the crop. There is more uncertainty in remote sensing algorithm. In some of the crop, because from remote sensing, we can actually find out the green or health. And in some of the crop, this may be poorly related to crop yield. So there may be some crops where they may appear to be too green, but that greenness is not directly related to what is going to be the final economic yield. Greenness may be related to the total above ground biomass, but it may not relate to the final economic yield. One example is like cotton. Cotton is an indeterminate crop. And many times the crop may be green, but due to pest infestation, it won't be having any flower or buds on the crop. So the crop may appear too green, better. And if we use remote sensing, we may expect that this crop is going to give us good yield. But there is another reason, and because of like pest infestation, there may not be any flower or bud which may ultimately lead to economic yield. So some crops, this problem is there. Another problem is that the crop signatures which we get from remote sensing, they are distinct, but they are not unique. So there is a difference between distinct and unique. Unique is something like your signature, that whatever you do, nobody else would be able to do. So that is unique, but our signatures are distinct. It means crop appear different from soil. Most of the green crop give this kind of signatures. But considering the type of heterogeneity of crops which happens in the field, like there are small field sizes, same crop may be sown at different times, there may be intercropping. So such kind of heterogeneity leads to confusion in the crop signatures from remote sensing. So that is another disadvantage. Another is that there may be noise in satellite data which we get. This noise may be on account of different kind of viewing conditions, because you can imagine that suppose if we have to do wheat yield modeling, we may start somewhere in mid to end of November and we have to go till March of next year. Now the sun illumination condition during November, then going to December, January and March, they are much different. The amount of radiation which is coming, and then finally it is reflected by the crop, which is sensed by the satellites. So the viewing conditions changes over time. There may be presence of clouds, which adds noise to the images, or any vegetation index which we derive from them, unless we correct for that. Or there may be presence of hazy conditions. There may be aerosols on account of especially pollutants. So that is another problem. So we need to normalize for such kind of noises in the data. And another thing is that we need specialized software and analyst requirement. So for crop yield modeling, not any run-of-the-mill remote sensing analyst can do it. It needs very specialized software, a domain knowledge of the agriculture, crop growth, soil, and then of course remote sensing. So there are some positives of using remote sensing for crop yield modeling, and there are some negatives. So if we divide the whole yield modeling approaches, which I have understood over time. So we are modeling, basically model means you are trying to estimate by any other mean except going and measuring it in the field. So that is what I call it modeling. So we do growth and yield model. Basically, broadly, there are two categories. One is empirical yield modeling and another is crop simulation yield modeling. And we are going to talk of both of them in today's lecture. Normally in agronomy, when we were doing our BSc agriculture, many of you might be remembering that we used to develop a biometric relations, that what is the height of a crop at flowering, and that finally relates that we develop a relation with respect to the final yield. So that becomes a biometric relation. Or what is the leaf area index at the flowering related to the final yield, or the number of plants multiplied by the height at a given stage is related to final yield. So some of the biometric parameter empirically is related to the final yield. Another thing is you can use time series of yield data. In this biometric, there is no remote sensing. Similarly, there are time series models, trend-based models over time when you especially talk of a administrative scale models. So there is ARIMA and all those kind of things. I hope you would be knowing better than me. Then of course there are econometric models where the independent variables relate to the econometrics. They are more related to prices, availability, production, previous season, any other policy input, and all those kind of things. And just a minute. Hello.
Hello, Namaskar, sir.
Namaskar. And then when independent variables are related to those which are either primary meteorological variables or those which are secondary meteorological variables. And of course, IRI has done a lot of work in this area, where weekly, monthly meteorological variables are taken as independent variables like rainfall, temperatures, humidity, radiation, and many a time the correlation with the yield is taken as the weight and a new model is formed. So a lot of work has been done. So basically these are different kind of, depending on type of independent variables which we use to develop the yield model. So if there are some major plant parameter, then it becomes a biometric model. If it is based on time series, then these are time series model. If these are based on economic indicators, then econometric models. And of course, there are a lot of variations in that and development in that. I don't want to go into detail. And then there are, if independent variables relate to meteorological parameters, which may be a primary meteorological variables like temperature, rainfall, radiation, or there may be derived meteorological parameters like evapotranspiration, there may be growing degree days, heliothermal units. So then these becomes. And of course, when I say empirical, it could be statistical or machine learning. So anything. Broadly, what I want to say in empirical is that when you use observed set of pairs of data of yield and the independent variables, and then you develop that model either using statistical techniques where there are many linear, multiple linear, non-linear, then there are other techniques, or machine learning techniques like ANN, support vector machines, random forest, and so on and so forth. So they all we categorize as empirical because these are based on, because those machine learning models are also to be trained from the historical data set. Then once we use remote sensing derived information as an independent variable to develop the yield model, we call that as a spectral yield model. And this could be based on a single date information derived from single date remote sensing data, or it could be using multiple date throughout the season remote sensing data and developing a growth profile and then deriving that profile parameter to develop the yield. We will discuss both of them. Many times we have seen in literature that what people do, they may combine spectral with meteorological, spectral with biometric, or spectral with time series. So there may be a combination. So it is not that we only use remote sensing as an independent variable, but we also can, along with that, use meteorological data as independent variable, as well as can use some time series or trend-based model with the as independent variable, and that has seen to improve the accuracy of the model. Of course, you have to see that all your independent variables are not related to each other. So there should be heteroscedasticity in your independent variables. So this is one side of the story where you need to have historical data set at the scale on which you want to develop the model of both dependent variable, which is my crop yield, and independent variable, which may be remote sensing, meteorological, time series, biometric. On the other hand, there are crop simulation models. Crop simulation models are based on the science of crop growth and how crop and its environment interact with each other. We will discuss more into that. This crop simulation modeling does not need historical data sets. But what it needs certain experimental data set that the model could be calibrated, the model could be independently validated. So we will discuss about crop simulation models, but what is important in crop simulation model is that we put all the basic crop growth parameters in terms of physical equations. Like if there is a how much radiation is coming, how much is atmospheric CO2, given the crop growth stage, how much amount of photosynthesis would be produced. Once photosynthesis are produced, how much would be used by the plant for its own respiration? That depends again on the growth stage, and it depends on the temperature. Whatever remaining photosynthesis remain, that is used for growth. Out of that, depending on the growth stage, that photosynthesis may be distributed among root, stem, leaves. And if it is the growth stage is after flowering, then it may also go to the grains. So all those kind of equations which are related to having feedback mechanisms. So a lot of science is there. But as you can imagine that besides not only crop growth, it also depends on how much irrigation is given. So you have to write a whole module of soil water balance. That soil is divided into different layer, how much irrigation is given, how it is that water is going to percolate to different layer, and how different water uptake would happen. That depends on not only the atmospheric demand, but plant growth stage, plant water status itself, that will determine. Similarly, if nitrogen is to be applied, then in what way nitrogen is applied in the soil, whether it is in terms of organic matter or it is in terms of fertilizer. And if you apply fertilizer, some of volatilization, it may evaporate, some may leach down. So you have to write all those kind of physical equations to put the processes into this model. So what is good about crop simulation model is that a lot of our science, our understanding goes into these models. And so they are very good in simulating the effect of any external factor. But problem is that because it needs so many, there are so many equations and it needs so many inputs. So these simulation models are very difficult to apply at a very large area. For experimental farm where you can measure all the inputs and give to the model, that is okay. But our purpose is not that. Our purpose is to ultimately make it for operational uses in the farmer's field over a larger region. So for that purpose, the simulation models can be run for certain locations, but you need to have data from those locations. Or if you want to run it for a larger area, you divide your whole region into different grids and assume that each grid is uniform in terms of all the inputs which are required by the crop simulation model. Or similarly, you can run the simulation model as one run for the administrative region for which you are trying to predict the crop yield. Now here, this is what traditionally people have been doing, and many crop simulation models now provide interface with GIS so that these simulation models can be run spatially. But one of my own research area for long has been how to assimilate or link remote sensing data with these crop simulation models so that I need not to generate measured input data from the fields to provide to this crop simulation models. So the crop simulation models, spatial runs can be without remote sensing or with remote sensing. So once it comes with remote sensing, a lot of remote sensing information, which like leaf area index, soil wetness, crop phenology, we can derive and give into this model to correct this model for some of the errors in inputs. So this is the overall broad yield modeling approaches. And our main focus would be either here or it is how crop simulation models can be specialized with remote sensing. Is it okay? Shall we move forward?
Okay, sir.
Okay. At least if one says, and I am clearly audible.
Perfect, sir.
Yeah. So this is where our focus in this lecture would be. Now, just to give you a very simple statistical empirical model with single date data. So what you can do, suppose this is an area, on the left side is a satellite image, it is a false color image. And during something like maximum vegetative growth or around flowering, we have selected some farmers field. These are around 22 farmers field across some 3-4 villages. And wherever you are seeing the red, actually this is the wheat crop. Mostly at initiation of flowering, and this is our maximum vegetative state. And what you can do, you actually go into these fields at the end of the season, do the crop cutting experiment and generate the yield data. Once you have generated that yield data, then you can go back and take a satellite data, which is around maximum vegetative growth or flowering, and can develop this kind of a simple linear model. And you find that there is a very good correlation between the yield which you finally get, and you can generate some kind of a vegetation index out of this, like NDVI. So NDVI versus yield, you can generate data. And once you have generated this model, now you can apply to every other field to know what would be their yield. But of course, the R-square says it is 0.84. So something like 15 to 20% uncertainty, unexplained variance remains with these models. And many times that is not acceptable. So here what it is showing, that a small area, if I am taking, these are the fields which we use to estimate the yield. And then we have applied to every other field to generate a yield value between something like 2.1 tons per hectare to 4.8 tons per hectare. But this particular approach, which is an empirical approach, now here, because you have few number of crop cutting experiments, so we use statistical model. If you have large number of crop cutting experiments, you can train also a machine learning algorithm also. But here you need to do in-season crop cutting experiments. So here remote sensing basically is used, that whatever model has been generated from certain sites, that is extended to other fields or other sites also. So this is one simple example. So here you need to do crop cutting yield data for few selected plots in the study area, develop the empirical yield model between the crop cutting experiment yield and some kind of vegetation index, which you derive from remote sensing data, and then apply this model to all other crop fields in the study area. But problem is this kind of model for each area need to be generated every year, and still 20 to 30% unexplained variability remains, whatever technique you use to develop the model. So that is our experience. Then I told you this is an example of a single date, but we can also use remote sensing data because it is repetitive in nature. Suppose this is one satellite image coming for whole of, this is the normalized difference vegetation index for Asia. I am interested for India, so I extract my NDVI of that. And for every 15 days, I get the image. So this side is the time. So in time I am there. Then I suppose this is Punjab area. I am interested in Punjab, Haryana. So if I click in this Punjab and I bore through to see what is the value of vegetation index in time. So I'll get for each pixel at each point this kind of graph, where on the x-axis is time, decade means every 10 days. So sorry, these images are every 10 days. So I extract those 10-day images of my crop area of interest. And of course, NDVI shows that wherever the value is high, it is red in color, and wherever it is low, it is bluish in color. So NDVI is basically an index which is related to the health or greenness of the crop. So if I plot this vegetation index in time, I'll see that as from June onwards, this crop is growing. The value of vegetation index keep going up. It reaches a peak somewhere around September. In between, there is a dip that is most probably related to some presence of cloud or atmospheric noise. And then again, it comes down. And then next Rabi season, when it is sown, again, it shows growth. This is again, that dip is due to the presence of some kind of atmospheric noise. And then again, it shows growth and then maturity. So you see, if you have multiple images and you see the time series of vegetation index, it clearly shows typically a crop growth during Kharif and Rabi. And you see after Rabi, the vegetation index value is lower for a longer time, because this is the time during April, May, when the fields are barren. And then again, from June 2nd week or so, the sowing starts for the other Kharif crop. So this way now, if I click on every other point, I'll get this kind of a profile. Now using this profile also, I can actually generate a model. So I'm just, again, as an image I'm showing for Haryana, this is a coarser resolution data. So where each pixel you are seeing, it is squarish. This is something around 1 by 1 kilometer. So, and again, the data here is of NDVI. So we call it that as from mid-December to mid-January, it is becoming green. So we call it as green wave. By mid-February, it is becoming too green, Haryana, Punjab. Mid-March, again, it is greening. And then mid-April, it is browning and then browning. So because of this coarser resolution, we have a high revisit of satellite. And there is always, I had shown, there is a noise in the remote sensing data. So we need to filter that kind of noise before working on this and actually fit a curve, which we call it as a growth profile. And from that curve, we derive certain parameters. Those parameters shows the integrated seasonal growth. So instead of a single day remote sensing data, now we have used the data for throughout the crop growth season. And whatever parameter you derive from this profile, that relates much better to yield than a single day data. So basically, this is the kind of profile you will get. So you can actually put some logic to determine what is the start of the season and what is the end of the season. The slope of this curve, which is rising, is going to give you the rate of greening or rate of growth. And the slope on this side is going to give you what is the rate of browning or rate of maturity. You can integrate the area under this curve, which is called small integral. So it gives an idea of the total, how much duration photosynthetic activity happened in the crop plant. And also you can, from this, you can derive what is the maximum vegetation index, which could be a maximum greenness or maximum leaf area index. So such kind of parameters are derived from this crop growth profile. And mind it, it is for every pixel. So I'm just giving you an example that we did it for a long time back. We did it for Dehradun district. And Dehradun district, you know, is mostly either it is forested district or it is hill district. And there is only small valley area where the crop of wheat is grown, and the field sizes are really scattered, fractured, and smaller. So we wanted to see that can, at district scale, a coarser resolution data, when the field sizes are small and there is more heterogeneity in the field, still can a coarser resolution data can be used to derive a yield model or not? So we used a satellite which is called MODIS, and from that we derived a vegetation index. So we derived basically a historical time series of data between 2000 to 2010. We did some kind of filtering. Filtering is a kind of a curve fitting so that all those kinks which come in the growth profile due to the presence of noise in the atmosphere, they are removed. We also have to classify to see which are of our crop of interest. So if it is wheat, we have to derive that and then derive some phenology parameter. So this is kind of phenology parameter which is derived. So it could be a small integral, it could be a larger integral, it could be this amplitude, it could be again that left derivative rate of greening, it could be right derivative, which could be right derivative, which could be rate of maturity, and left derivative, which could be rate of greening. So there is a freely available software available in MATLAB. It is called TimeSat. So it can do this kind of data processing and derive all these parameters. So then once you have these parameters available at the district scale for each of the pixel, you can average out for the district. So problem is you are going to get profile parameters for each of these pixels. So here it is the crop of interest, wherever you are seeing the red color. And you have to average out to find a profile. And then from profile, you can derive all these phenology parameters. And then using any of the empirical approach, we use simple regression approach to develop a yield model. So this is something like how at a district scale, the yield, which is the reported yield by Department of Economic and Statistics, and the amplitude of the profile which we derived, how it relates. So you see, there is a good correlation. It appears both are moving in similar direction. Similarly, right derivative, which is the rate of maturity, and the small integral, which is the total area under the curve, how over the years they relate. So there is, we find that they are relating well to the variation in yield at the district scale over 10 years. And of course, we found that maximum R square, if we relate wheat yield versus amplitude, R square was 0.69. And this is how it shows that if we use only a single day data for each of the year of the vegetation index value to develop a yield model, the R square was 0.179. Once you filter the atmospheric noise and then use the single date from 0.179, it improves to 5.551. But still, many of the years are related in one corner and two are there. So it is still not a good model. And when you use profile-based amplitude, then there is more better distribution of yield versus amplitude. So this is what it is showing, that how in each of the step, when we do pre-processing of the satellite images, it improves the relation. So this is finally, this is a remote sensing and time series based yield model, where from the profile, from multi-date, we derive the amplitude. And because over time, there is a trend in the yield in the wheat at the district scale, so time is also used as an independent variable. And after using all this, the R square is, you see, is 83%. Again, 15 to 20% is uncertainty. The standard error of estimate was 123 kg per hectare. And the final yield model, how it performed, the blue colors are the observed yield. The dotted red line is the predicted yield by the model. And then this is because up to 2010, we used the historical data to develop the model, it should give better. Then we started for 10 and 11, we actually forecasted we actually predicted. And when the yield was reported, we found that for at least 10, 11, we had a good correlation. Then whatever we predicted beforehand, like by the end of March, that is what the state government nearly gave that value, around 2.250 tons per hectare. So This is one way, but it is quite data intensive. You can imagine that you have to take historic data sets over time, every 10 days, every week, fit out the profile, derive the profile parameters, average it out over a region, and then relate it to your yield. But this way it works much better than using a single date remote sensing data. The similar approach we did because there was in between requirement that can we do Haryana, Punjab fast? So, and we wanted to develop the model to predict at district scale. So what we did, the districts were divided, were aggregated as per agroclimatic region. So in Haryana, Punjab, there are 3 agroclimatic zones, zone 1, zone 2, and zone 3. So whatever methodology I had shown you in previous example, the same methodology was used. And here we used again regression analysis, simple statistical technique. So for zone 1, this is how the amplitude of the profile versus the yield relates. For zone 1, where the R square was 0.58, for zone 2 it is 0.75, and for zone 3 is 0.78. And you can see the number of observations we used were 84, 116, and 110. The RMSE was around 500 kg per hectare. And error was of the order of 10%, 10 to 11%. And the district scale for Haryana and Punjab type of states. But using these models, we were able to, this was much older study which we did at IRI. And we forecasted using satellite data up to 20th March. So whatever we predicted and versus what later estimates given by State Department, DES. So our error was in forecast was only 3.4% underestimation for Punjab and minus 2.75% for Haryana. So, and of course, because when you have to do a forecast of production, you need to multiply your forecasted yield with the area, and remote sensing is good in estimating the area. We are not covering the area part here, but area can be easily estimated using different classification algorithms with some ground truth available to you. So this was basically an empirical yield modeling. But again, the problem is you need to have historical data sets. And these models cannot predict any extreme value which was not present in the history from when you develop these models. And we have seen that average errors are 10% and explained variability is only 80-85%, maybe less than that also. So for many applications, they are not acceptable. They want a accuracy better than 90%. And another problem is there that still you are not able to do at a field scale. This you are doing at administrative scale because historical yield data are available only at administrative scale. And the problem is when you estimate a crop yield at administrative scale, then all the variability average is out at the administrative scale. Suppose you are estimating an average yield in a field versus average yield in a village versus average yield in a taluk or tehsil versus average yield in a district versus average yield in a state. So as you move to a larger administrative region, the variability start averaging because you get all kind of lower, higher value. So law of central tendency works there. Everybody studies that in statistics. So with these some shortcomings there, we go to another approach where we put a lot of science in developing crop modeling systems. So you may be aware that Indian Agriculture Research Institute is the only country in the India which has its own crop simulation model. Otherwise, there are mostly coming from outside India, like DSET series of crop models, APSIM from Australia, then EPIC from US. Then there are from European system also in DSET, many models have been, different crop have been integrated. So, but in India, we have our Department of Environment Science has been at the forefront in developing and improving a series of crop models under a brand name called info crop. So these crop models are available on IRI website also with a graphical user interface. You need not to look into the details. Inside, it will ask you some inputs, ask you some weather, what type of soil is there, which variety. And if you don't have, even you tell your location, there is a database where it can pick up many things. Suppose you don't have the properties of your soil. What is the bulk density? What is the hydraulic conductivity? What is the depth? So still we have put in a database that if you tell your location, it approximates what is the type of soil may be present there. So where it simulates the effect of major yield regulating factors like weather, where it needs input on rainfall, temperature, solar radiation, wind speed. It needs information on which crop and what is the type of variety of that crop. So it means it needs information on the physiological characteristics of the variety, phenological characteristics, and morphology. Then it needs a lot of information on soil on which the crop is growing, like what is the texture, pH, depth, fertility status, in terms of organic carbon, available nitrogen, available phosphorus, and the type of agronomic inputs put into that which seed, what depth of seed, what seed rate, whether farmyard manure, how many time of irrigations given, whether it is flood irrigation, sprinkler irrigation, drip irrigation, fertilizer is 1 split, 3 split, what is the dose and all that, and management inputs on date of planting, fertilization, irrigation. So you can see that model works good, but it needs hell lot of inputs. So much inputs can only come from a very detailed measurements at the field scale. And so these simulation models have more or less have remained as a scientific tool with the scientists only. So though they are good, a lot of science they put into these models, but because of their high data requirement and that too kind of data which is not easily available, their applicability at regional scale has been always limited. So in this slide, I just want to give you an idea of what goes into a crop simulation model. These are process-based and dynamic in nature. It means they simulate the growth at constant time scale. It could be a 1 day, like InfoCrop do the crop growth at 1 day interval. So it needs input, especially that of weather at 1 day interval. Every daily weather data, it needs to run the model. And it is based on quantitative understanding of the processes which goes into soil, atmosphere, plant. But it integrates all the things, soil, weather, crop management factors together. So their predictive ability is good, but because they are input data intensive, their applicability at regional scale is restricted. So this is one problem. And this is called a schematic diagram of a crop model, how it is given. Suppose there is atmospheric CO2, there is radiation coming, and based on temperature, there is a module which also tells about what could be the development rate, and based on that, what is the development stage of the crop. Because you need to know whether crop is in emergence, whether crop is in jointing, or it is in vegetative stage, it is in flowering stage, it is in maturity stage. So this basically runs based on what is the temperature. And given a development stage, given the radiation, given the CO2, it will calculate what is going to be the assimilation of CO2 in terms of photosynthesis, how much glucose or sugar are produced. So out of that, depending on the atmospheric temperature, there would be some maintenance respiration and some losses of that photosynthesis would happen. Rest, whatever they're there, they are available for growth. But once the plant convert as a process from glucose to proteins to fats to higher carbohydrates, there is again growth respiration. So this growth respiration, again, it removes. And whatever after that is available, it is available to be partitioned among leaves, stem, panicles, and roots. And partitioning, how it depends on what is the development stage. And once those weights are calculated, depending on the stage, from leaf weight, you can calculate how much is going to be the leaf area index. And based on that leaf area index, for the next day, you again run this module. So this is only a simple crop growth module. There could be soil, atmosphere, fertilizer, pest, so many things. So our basic premise of using remote sensing with this model is that if we link within season observations of crop growth or crop environment, which is estimated from remote sensing, with this crop model, then that linking may steer the model on the correct simulation path and may compensate for many of the errors which are there in the inputs. Because for each field may not be knowing so much inputs. So this is one example long time back, predecessors to InfoCrop, there was WT Grows. And this is one example where we had only specialized a crop model like WT Grows. It is a wheat growth model in a GIS environment. So what we did, that it would ask for what is your study area, and once it knows the bound, it will ask you at what grid size you want to run the simulation model. You also need to provide the administrative boundary map, how many number of districts, tehsil, whatever you want to know. From remote sensing, we need to provide also what is the classified area map, where is the crop, then daily weather. Daily weather is coming from stations at point, some weather constants, soil map coming from NBSS LUP, some soil organic carbon to initialize what is the fertility of the of the soil. Then for each grid, or because this system used to run on grid, for each grid we were not knowing which cultivar, which is the sowing date, what is the irrigation fertilizer. So only at district scale such kind of inputs are generated, provided in a GIS environment. In GIS, it generates overlay a grid, apply the crop mask, and find out only those grids where your crop of interest is there. For on a given day, how many weather stations are reporting the data, it will interpolate them to generate the surface, so that daily weather spatial files could be generated. Soil texture map, depth class map, organic carbon by interpolation would be generated. And of course, depending on the grids lying in whichever district, they would be assigned. And this whole data is transferred to a link to a central database, which is in a RDBMS, and where each grid number is defined. Its central at long is also stored as an attribute. What is its geographical area? Define a unique grid number and to which district it belongs, because we were providing administrative boundary map. In each grid, what is the fraction of crop of your interest which is coming? Each grid, which is the corresponding weather file? What are the weather constants for that grid? What are the soil water constants? So from soil texture class, applying some pedo transfer functions, we calculated soil water constants because these are needed by the crop model. Then similarly, what is for each grid, what is the average soil depth? For each grid, what is the organic carbon content? For each grid, based on which district it is there, what is the dominant cultivar? So cultivar properties, what could be the median date of sowing, what is general practices of management of irrigation and nitrogen. So this all comes into that, and then there is a interface program which for each grid run this crop simulation model. So you can assume that for each grid, this model runs for crop growth for 120, 130 days, give the outputs, this output goes back into the GMS, and that could be visualized back as a crop yield map in a GIS, or could be aggregated at the administrative boundary to find out what is the crop yield. So this is one example where simulation model is used, where GIS technology and remote sensing is used to specialize the crop model. So this is the kind of output. So this we did it for Haryana, and each grid was 5 by 5 kilometer, and all those inputs would be generated, put in the GIS, and then goes to central database, run for each of these grid the simulation model, and finally it would generate a yield value. But you see some kind of artifacts are coming, like this whole area is appearing to, because this is one district. This may be one district. This may be one district. So depending on management practices which are there. But now it is generating for each grid what is going to be the crop yield, 3.5 ton to 4.75 tons per hectare. And I'm only showing you one output as a crop yield, but it generates so many other outputs. So such kind of maps could be generated by specializing the crop yield. And then in this system, we found that from remote sensing, if we find out the phenology and link into this system, because we were knowing the sowing date, average sowing date at a district scale. We were not knowing for each grid what is the sowing date. So what we did, we used multiple data sets. Similar to that, we have vegetation indices, generate a profile. Now in remote sensing, the problem is when the crop growth is there, this is very clearly visible. But in the initial stages, when the crop is small, you cannot, remote sensing has more uncertainty. And our purpose was that phenology means we wanted to find out what is the date of sowing in each of the grids. So what we did, that we run the simulation model with different date of sowings and try to match the growth with the NDVI profile. This is the NDVI profile, this profile. So wherever for which date of sowing, we get the same maxima in our model simulated value, and we chose that as the date of sowing. So this is just an example at district scale, that if you simply run the model with all those inputs which I had shown you in previous slide, so observed yield versus simulated yield, you won't find any relation, much relation. The correlation was 0.163. Of course, the RMSE was low, around 404 kg per hectare. But once district-wise you define the irrigation and nitrogen, so R improves from 163 to 0.16 to 0.53. And once you also add the simulated phenology into that, it becomes much better. Now R is 0.74, but there is a constant bias also we are finding. This is 1:1 line and it is underestimated. So, but anyway, what it shows is that if you can use remote sensing data to derive the phenology, it improves on this spatialization. Now I'll come to another study which we conducted where our interest was a field scale estimation of crop yield. And this is much detailed study one of my PhD student did. So on the right side, this is the Google Earth image in the background, true color. And on that, we actually digitized the each survey or Khatani number of that village and selected some of these white colored patches which you are seeing. These are the fields which we selected and which we monitored very intensively. So this is one village and there was another village, Lokra. So this is only one village, Lokra village, another was there. So we had some ground observed fields also, and these are farmers' field. And you see the plot size, it means square meter area of whatever we selected. So it was medianly, it was something like 4,200 square meter is the field size. That is the median where 50% cumulative frequency is there. So in these fields, what we did, these are those fields in Lokra, Mumtajpur. In not only one, but in 2 years, we did this study. And a lot of survey data we collected from the farmers. And we found that variation in sowing date for wheat was between 1st November and 25th December of the selected fields which we had taken. The farmers were applying nitrogen as low as 70 kg and as high as 195 kg. The seed rate varies between 87 kg per hectare to 150 kg per hectare, though recommended is 100 kg per hectare. And the number of irrigations provided were varying between 4 to 6. So you see among some 40-50 farmers field itself, there is a lot of variations. But this data was collected. And what we did, we took that InfoCrop wheat model. And for those farmers field, given all the measured inputs. So we measured the soil properties, when how many irrigations farmer has given, how much fertilizer he has given, in how many splits he has given, which variety he has sown, what are the variety characteristics, what is the date of sowing, what is the depth of sowing, what is the planting density, and all those inputs we provided to this model, and we found that model was doing a good job, provided all measured inputs were given. So days to anthesis means days to flowering. We had a very high correlation. The error was only 3%. Days to physiological maturity, the error was only 2%. The index was 0.98. The total above ground biomass error was 4%. And of course, in the yield, which model was able to simulate, was with 6% error. So what I want to say that these crop models, even if it is from farmer's field, if you have all given good measured input to the model, it can do a good job of prediction. Okay. And similarly, the model in 2 years was able to predict, you were able to simulate good leaf area index. Leaf area index means number of leaf surface area on one side divided by the ground area. So it is a measurement of how many number of leaf layers are there. So observed leaf area index versus simulated leaf area index was also good simulated among those fields, in both the years. So around 13% was the error. Now, this is the overall methodology we developed, where we used remote sense. It has two modules: remote sensing module, crop simulation module, weather forecast module, and then there is a standard database. So in remote sensing module, what we did, we took satellite images, and using another physics-based model, which is called radiative transfer model, we generated some canopy or wheat crop parameters, biometric parameters, like what is the leaf area index, what is the leaf chlorophyll, what is the leaf moisture. So remote sensing, I want to emphasize here, is going into the direction where we are not doing an indirect estimate, but now we are trying to estimate the biophysical parameters, whether of soil, whether of crop, whether of ocean, whether of water, or whether of atmosphere. So I'll tell a bit detail about there. I understand that today's presentation becomes more technical, but I cannot help with that. I told you this is a much technical subject, how we do it. Now, whatever outputs are generated at different dates from remote sensing, this we assimilate into crop simulation models. So there are two different techniques we used. One is called forcing techniques, another again statistical technique. It is called ensemble-Kalman filtering technique. So leaf area index and phenology, these two, phenology adjustment, these two inputs which we derive from remote sensing images, they are assimilated into crop simulation model. Now, if you want to do a crop yield forecasting, so you have to forecast the weather. So for that, we run a weather forecasting model, which is called WRF. It is what is run by India Meteorological Department. It is again numerical weather prediction model, which generates a 15-day forecast. But whatever forecasted weather comes from this, there is always a difference between observed and forecasted. So using historical observed and forecasted data, we developed a weighted adaptive bias correction approach in real time. So from remote sensing inputs come, they get assimilated into crop simulation model. Then weather forecast comes into the crop model. And then there is a database on variety, weather management, soil properties. So here, important thing was that for each of the fields, we are not defining which is the crop variety, what is the soil type, when it is sown, what is some average values have been defined for that. But the corrections for those errors is based on this assimilation to produce the crop yield or crop yield map or crop yield forecast map. in a GIS model. So this is the overall methodology. So this is just an example that is on when these are our fields. Initially on 4th December, we are finding crop wherever you are seeing red color, this is the crop. So on 4th December, only few fields we are seeing red, and this is actually mustard. This is not wheat. This is actually mustard because by 4th December, it is already in, because it is sown in mid of to end of October. So by 4th of December, it is already very sizable growth and we find. And by like 5th January, you will start seeing reddishness in other, which where the wheat is growing. By 22nd of February, wherever these mustard was there, these are already started maturing. And the wheat starts becoming more and more green. Here it is red. And by 9th March, again, this situation. So multiple times. And this is the classified map. Wherever you find green, it is wheat. Wherever is yellow, that is mustard. And wherever it is black color, it is the other category. And this in between area, this is the village area. And this is the village pond. So there is water here. There could be cloud shadow or water here. So on multiple dates, we analyze these images and generate for each of the field what is the leaf area index, whether it is between 1 to 2, 2 to 3, 3 to 4. And also like for each of these fields, what is the chlorophyll content in the crop. So this is just an example of what we retrieved using another radiative transfer model and what is the observed LAI. There is a good correlation between them. And as the crop grows, the leaf area index increases and decreases. So on different days, we have the observation. And of course, I don't want to go into this detail. How to do the correction, atmospheric correction because of the remote sensing images. How to remove atmospheric noise. Different models have been compared and we found that the model which we were using, it is able to do much better correction of the noise in the images. So our retrieved LAI is much better related to the measured LAI as compared to what is used by a different model. And this model is used by European Space Agency. So, but we didn't use their model. We used this model to do the correction. And similarly, for deriving the leaf area index, we used ANN versus a lookup table approach. And we found this machine learning algorithm does not work good. Rather, the traditional lookup table approach works much better to estimate the leaf area index. So this is all. And we also found that which are the number of bands which improves the accuracy of LAI retrieval. So we found that inclusion of red edge bands, they improve the accuracy of LAI retrieval. So these all relates to how good and how accurately you estimate leaf area index or leaf chlorophyll or leaf water. So this is kind of image of what is the leaf area index. We had seen other from a different satellite. And this part we had published in a paper also, Elsevier Journal. This is an example where a nested weather forecasting model was set up where the outer domain is 900 kilometer, inner is 300 kilometer, then is 100 kilometer, and finally at 1 kilometer. So we were able to forecast weather at 1 kilometer resolution. And we used a adaptive weighted function where based on the error which are closer to forecast, they have a higher weight, the lead time, and the days which are farther from the forecast in history, they have a lower weight. So this is to correct for the weather forecast. This is just to give you an example. This red color is the forecasted, whereas the blue color is the observed value. So you see there is a lot of difference between forecasted weather and observed value, especially during this period. So there is error of more than 5 degrees centigrade. So, but when we used our weighted adaptive correction approach, so which is of violet color, so it is coming very close to observed. Or whether you see global radiation, the WRF model, weather forecasting model, was all the time overestimating, and this is the blue color is our observed. But our weighted bias correction also brought this forecasted weather closer to observed. or similarly for T mean or for vapor pressure. Vapor pressure model was underestimating and observed values were higher. So all those kind of corrections also needed. So a lot of science. Now the basic purpose here is how to assimilate remote sensing derived leaf area into the crop model. So what is happening? Crop model also estimates leaf area index inside, it simulates. So what we do that on a given day, from remote sensing our leaf area index has come from a field, we tell the model that this is the leaf area index, take this and next day onwards start simulating your growth using whatever leaf area index we have given you from outside. Why? What is the purpose in that? Purpose in that is that because we might be having error in defining the date of sowing. We may not be knowing what is the number of irrigations he has given, what is the soil properties. So we have defined some soil property, but there may be errors. We have defined some variety, which actually farmer has not applied, but that may be an error. So all those errors, so model starts simulating and it will simulate. But on a day, like 40 days after sowing, from remote sensing, we find actually LAI should be only 1.5, but model is simulating something like 2.8. So we tell the model that on 41st day of growth, you take our value and start simulating. So it will simulate. Why this has come lower? Because this is observed value. So there may be situation that LAI, the crop growth is lower, the seed rate was lower, the sowing date was late, crop has not grown. We had assumed he has sown on 15th November, but he might have sown on 20th December. So it has been able to correct for that. And again, on this day, we find that actually the LAI should be 2.5, but still it is simulating 3.5. So we tell that. So this way, we have tried different kind of combination that on 40th day after sowing, we changed it to 1.3, to change it, increased it to 4.4 on 70th day. So multiple time as and when you put into the model will keep changing its course based on the observations which comes of LAI from the remote sensing. So finally, what happens that whatever final biomass is produced, that would be different because now the model goes on a different course. So it would have, the model would have gone and predicted something like 13 tons above ground biomass. But once you have reduced LAIs, based on LAI, you have reduced the growth, it is going to produce only 8.5 tons. And coming this from different methodologies of assimilation. So now these farmers' field, I'm just giving example that when those farmers' field, we have defined the same input, same weather, same soil, same variety, same date of sowing, same management. All farmers' field model is going to simulate the same value of above ground biomass or same value of yield. Okay. Mind it. All the farmers' field, we are giving the same input. So model is going to produce the same output. But once with that, we assimilated using forcing or ensemble Kalman filtering, the satellite derived leaf area index. You see now this is 1:1 line. Now you see the blue dot started aligning along the 1:1 line. So this point has come here. This point has come here. This has come here. This has come here. So they started aligning along 1:1 line. It means assimilation of in-season remote sensing data is able to compensate for many of the input errors which we were not knowing. Here we have deliberately put it, we were knowing for those fields, but we didn't specify it to model. Okay. So this proves that whatever our thinking was there, our premise was there, our logic was there, it works. Then we did a lot of type of different experiments with these experiments, and we found that experiment number 11, which is, let me go to previous. Experiment number 11 is that where initial soil moisture, we have fixed it. Soil parameter fixed. It means fixed to all the farmers' field. Irrigation, same fixed value. Fertilizer, same fixed value, all the farmers' field. date of sowing fixed value all the farmer's field, and LAI assimilation we are doing through Ensemble-Kalman filtering. This is again a data analytics technique. And then phenology adjustment also based on remote sensing data. So by using that, we are finding that in grain yield, this type of experiment is producing the lowest RMSC of something like 350 kg per hectare. So same was for total dry matter or phenology, days to enthesis and all. So then we applied this whole technique over a larger area to all the fields. So as the leaf area index started assimilating at 3 different days during the growth season, this is the final crop yield map for each of those fields, varying between 2.5 to something like 7 tons per hectare yield. It is showing, and it shows that initially we were having an error of the order of something like 20%, which as more and more remote sensing derived leaf area index get assimilated, it is coming down to something like less than something around 7 to 8%. In total dry matter, it started with something like 8% and it remains to 5-7% in both the years, whether you do it with actual weather or whether you do it with a weather forecast. So we compared that also. So when you use weather forecast, you can actually forecast the yield also, at least 15 days in advance. And this whole system, we have developed a Python framework. It is available on our team's website. This is a point scale implementation, and then we are trying to make a software which will implement it spatially. So IRA crop simulation model, InfoCrop, the radiative transfer model, ProSail, and Ensemble-Kalman filtering technique, remote sensing data assimilation, and all that. We are expecting that this we would able to implement for a larger region. The problem is coming, we need really a high power computing system and data analytics to be done in real time, because a lot of satellite data, if we want to work for a group of districts or for a state, and somehow that facility yet has to come up within ICR. Though within ICR, we have developed some kind of cloud, but that when it would be available to us for doing this implementation, that is a matter of time. We are waiting for that. So this we can skip. Then this we have tried to use these techniques for our crop insurance also. So in crop insurance, basically, there are 2 kinds of schemes under Pradhan Mantri Fasal Bima Yojana going. One is based on the yield index insurance scheme, that is for major food grain crop. Another is based on horticultural plantation crop, that is based on weather. And earlier, before 2016, even there was for food grain crops, there was weather-based crop insurance scheme was there. But with 2016, with PMFBY, they had changed it to only a yield loss-based insurance. So basically in all insurance, what you do, you need to develop a relation between change in yield versus some kind of parameter based on which yield is related. So whenever the change in yield become negative based on that parameter, we call it the trigger or strike. So this kind of development of relation is called historical burn analysis in insurance parlance. So, and when this becomes 90 up, then once it starts, the yield change becomes minus 90, it goes to minus value, your trigger or strike starts, and once the value reaches to 95th percentile, you stop loss. It means maximum loss has happened and payout has to happen. So here, like we had used a weather-based index, which is extreme maximum temperature, number of days when during a particular growth stage you get extreme maximum temperature. It means that maximum temperature above 95th percentile based on historical data. So you see the relation between change in yield and number of extreme days, there is more and more negative change in crop yield. This is at a district scale. But correspondingly, if we develop a relation with vegetation health index, which is derived from remote sensing, then you find the R square, which was for a like extreme maximum temperature was 0.44. Wheat is very sensitive to the terminal heat stress. So it is during that flowering period. So a remote sensing derived weather health index is much better related to change in yield. So whenever the VHI values goes below a critical threshold of something like 50 or so, the yield become negative, and you see R square is 0.73. So we developed a whole term sheet for these insurance plans using remote sensing data. And we showed that the R square of yield lies to payouts in our scheme based on remote sensing is much better. The false triggers percentage also reduced, and the basis risk is also reduced. So these are, if I hope some of you would be involved in crop insurance type of research or work, so you would understand and appreciate that. I'm not showing the whole term sheets, how we developed this, but this is what we proposed to the PMFBY. I'm part of the technical team to provide inputs to the PMFBY. But still, because it is based, still they are not changing it to a yield, from yield insurance to a remote sensing index based approach. Another problem in crop yield insurance is to estimate the yield loss. So you have to, because the current scheme is based on yield loss. If yield loss is happening more than 10%, then only the payout happens. 10% is the basis risk, less than that, no payout happens. I hope many of you have traveled or taken a health insurance or travel insurance. So you know that when they say that if you go out and you fall sick, so for first $100 payment of medical treatment, you have to pay from your own pocket. But if it is more than $100, so whatever more than $100 is there, that would be paid from the medical insurance. So same is in case of crop insurance. So up to 10% loss in yield is not covered. If it is more than 10%, then only it is covered. So it means you have to estimate yield with very high accuracy. So here what we did, we used again the radiatory transfer model, which is a canopy radiatory transfer model, which shows that if radiation comes and fall in this crop, it will go under various reflectance, scattering, and then it will be going back to the satellite. And satellite is able to, this is the satellite image, and using this model, we are able to estimate leaf area index. That we did it, I had shown in previous example. But now we are making it a more simpler. Then what we do, we bring in our infocrop model. And for that given region, it could be a district, we try to find out what is the range of date of sowings, what is the range of seed rate, what is the range of fertilizer and irrigation which is given in the field. So we run the model with all those different scenarios of different date of sowing and combinations. And we generate a library of crop simulated growth realizations. And based on that, we generate on the day on which we have satellite, on the same day from the model, we generate what is the leaf area index. So this is a model generated leaf area index. And then from remote sensing also we have a leaf area index. So what we do, we develop from the model, we have generated the simulated leaf area index, and model also generate a simulated yield. So for that date LAI and what is the relation to yield, we generate a biometric model, a simple regression model between a simulated LAI, like 88 days after sowing, model is simulating some LAI and corresponding to what is the yield. So the relation between them is developed as a regression model. And once you have developed that regression model, from simulation, from remote sensing data, now you have a yield, you have a leaf area index image. And you have a model where leaf area on that day versus yield, what is the relation? So you apply that. So like we took this example, there were 3.2 million pixels in one district like Ganganagar. And historically, we were knowing based on DES data, Department of Economics and Statistics data, which was a bad year, which was a normal year, which was a good year. These were the yields reported by them, 2.85 to 4.17 tons per hectare. So we tried to run the model in this approach for this whole district. So this is the whole Ganganagar district. This is the international boundary. Wherever wheat is grown, and I'm a small area, if you zoom in for each of the field, you can see there is a red color means it is showing there is a 10 to 20% loss. This darkish red is more than 20% loss. Poor means wherever yellow is there, yellowish green, it is 10% loss. Where green is there, it is good. Wherever blue is there, it is better than 20% as compared to normal. So this kind of maps we could generate. So for 2009-10, we found that more and more fields were under red. It means exceptionally poor to poor. Whereas in a good year, more fields were under green and blue for the same area. So if you see overall for the district, number of how much total area. So in a poor year, more area was under very poor, exceptionally poor and poor category, and less under good, very good and exceptionally. Whereas in a very good year, there was very less area under exceptionally poor or very poor, and more under good, very good and exceptionally good. So vicariously proved our methodology. And of course, this we can skip. This does not belong to here. So now way forward is that we are trying to work in implementing an operational system where LI retrieval and assimilation into crop models with weather forecast all get merged together. And you can understand that weather forecasting, if you want to do a large area, you need a supercomputer. This model does not run so easily. They need a lot of computation. And they need a lot of global data also, because the weather at a place is also determined by many global weather parameters. And we need to develop a system which will converge the evidence in season from ground observations as well as from satellite, like in season vegetation indices, crop condition, vulnerability. And we need to develop capacities of students in making use of such kind of data and tools for real world applications. Thank you all for your patient hearing. I'm again say that whatever I tried my best, but this becomes a higher level of technical presentation because the problem is also greater. So if you have any questions, I can handle that.
Thank you very much. Just unshare your screen. I think that would be better. Yes. So chat box, one question is there basically.
Yeah, that I can understand.
Okay. And anyone else would like to ask some question?
It says, sir, can you throw more light if possible on the role and relevance of remote sensing techniques in crop breeding experiments?
Yes.
How successful are we in getting the real estimate? What is the forecast error percentage when it comes to CCs, so that we can take them with a pinch of salt? Yeah. Currently, whatever CC is mostly are happening for what is called, it is used for census. Census in the sense to estimate what is the crop production area yield at a district scale, and the whole crop breeding experiment, sampling plans, stratification and all has been developed for different crops in different region by the ISRI, Indian Agriculture Statistical Research Institute. So that was for doing the advanced estimates. The purpose was for advanced estimates. But under crop insurance scheme, again, the requirement for doing crop breeding experiments increased tremendously many folds, because now your insurance unit is a village or a village panchayat, which was not in case of advanced estimate. So in case of crop breeding experiments, the number of experiments increased tremendously to be done. And the data is also to be reported in time, because unless that yield data is reported in time, it is checked for quality. The crop insurance companies are not going to make a payout whether there is a loss in yield or not. How to estimate loss in yield unless this CCE data is coming? So this became, so whole Pradhan Mantri Fasal Bima Yojana, which started with a very good mandate that we change it to a yield loss based insurance, has entered into another trap. How to objectively and with high accuracy estimate the yield loss. And now the whole scheme is struggling with that, and that is why many of the states have withdrawn from this scheme also, because they were finding that this doing business of CCEs, and that to so many number of CCEs, and CCE doing is not easy. Suppose you develop a plan, you do a stratification, you develop a sampling plan, and you go into the field and say, and farmer says my crop is not yet mature. And other farmer, you go and they say my crop was matured, I have already harvested. So practically it is a very tremendous time consuming, energy consuming task. And also I exactly cannot say what is the error, but there are a lot of uncertainty, maybe of the order of 30 to 40% in whatever yield we do estimate based on CCs. Now coming to the question. So this was the background of CCs. Now coming to the question of remote sensing for CCs. 2 years, our Mahalanobis National Crop Forecasting Center, which is a Ministry of Agriculture ISRO combined center. It is located in our campus, and our good old friend, late Dr. S.S. Ray, he led this effort where the crop cutting experiments sampling plan was designed using remote sensing data, because you have in-season remote sensing data. So you can actually, and you can stratify the areas into agroclimatic zones or based on any other criteria, and define the grids which are showing good crop growth, poor crop growth, moderate crop growth. And then randomly they were able to select, tell the coordinates, and they would able to tell these are the crop cutting sites based on remote sensing data. And if this site is not available, which is the alternate site? And if even that is not available, what is the other alternate site? So for every crop cutting experiments, 3 sites were given: priority 1, priority 2, and priority 3 from remote sensing. What is the, I expect, actually I am not yet privy to the final results that how much it was able to reduce the errors. But I am privy to this, that they had made up this plan and cropping experiments were done under the edges of PMFBY, because I'm also involved in some technical aspects in that. That remote sensing based sampling plan for cropping experiments was expected to reduce the results, but I really don't know. Finally, results, I have not seen what happened in 2 years, whether it was reduced or not. So does it suffice to your query?
Yes, sir.
Okay.
Would like to know more about the challenges that we are facing, sir, while accessing data.
Yeah.
That during remote sensing, what challenges do the researchers face?
Access to remote sensing data is now not a challenge. And provided if you have money also, you are supported by funding, then it is, I say, it is non-issue. Because now you can go to private agencies which are already there, and many more are in the pipeline. I hope you would be aware that Government of India has initiated a lot of reforms in the space sector, where involvement of private sector, startups, their involvement, not only in developing rocket satellites, but their applications. So data availability is not a challenge. The challenge is coming how to convert this data into the information based on which you can take a very informative decision. So there, we are finding very less kind of people who can actually understand agriculture, crop growth, who can understand remote sensing, data analytics, uncertainty, weather modeling, and all. So problem is such kind of people are rare to get, who understand so much complexities, relate them, and also can do computer programming, use computer softwares to handle them. But if you want to scale them out, there is constraint of computing facilities, storage facilities, and all. So data availability side, the challenges have become minimal. Of course, the problem in India, one is there that optical data is getting contaminated with cloud. So you have to many times switch over to the microwave type of remote sensing, which is more challenging and difficult to understand and needs some specialized software for its processing. So that is the case. But this is a challenging field. This I started when I used to do PhD, how to link remote sensing into simulation model, and still I'm continuing with this. We have reached a level of maturity and understanding. But you can see, I say that yield is a very, what to say? It is a very a deceiving kind of thing. And the thing which is not perfect, which is not fixed, estimating or predicting that becomes more challenging. Why I say yield is a very deceptive thing? Because yield of a plant versus yield of a field versus yield of a group of field versus yield of the same crop at a village versus yield of that same crop at a district versus yield at a state versus yield at a nation. These are all different numbers. So it is still a challenge, and it is not a challenge for us. It is globally, it is a challenge. People are working. We are interacting with European group also. There is a Mars program. They have a Mars program. I had visited to their joint research center in Italy also. They had invited me for showing our work and how we are progressing in this direction. So that is what I want to respond to that.
Yes, sir. Thank you.
Yeah. Any other query, comments? Dr. Rajni?
Yeah.
Your comments.
Oh, it was a really very nice session. In fact, I would just like to know, we have these NDVI, estimated NDVI is also available nowadays. So you are estimating them on your own, or you are using those also?
No, you can.
I mean, which one are much better?
No, I told you from many satellite historical long series are available. Still, you need to do some kind of pre-processing and noise removal when you want to use them. It is not directly usable, as I had shown you.
Yeah.
So that is
NDVI is also.
And if you want to do it a real time, suppose this, now you want to forecast this season wheat yield. So you need to have a real-time data like which we get from our satellite station. But anyway, that is not an issue nowadays. Within 1 to 2 days, many of the data is available. But a lot of pre-processing is needed, which needs some computation and analytics understanding also. It is not that data is available and you can directly.
And you can use it, right?
And of course, our, as I had shown, our purpose is not to, because we had seen using whatever technique you use, empirical models have that uncertainty. And only the simulation models have that ability to provide us good estimate. But simulation models have the problem that you need a lot of inputs of everything, and how to compensate for that field scale inputs from remote sensing. That is our area of research. And we have been successful to a lot. I had not shown, we had last year published a paper in agricultural system also, which is a Elsevier highly rated journal in the area of simulation modeling. So this we had shown there. So and now actually now we are looking forward how to how to operationally, but because my interest is very simple. My interest is that we say we have running a system in a cloud and we provide an interface. A farmer goes into his field, opens an app and mark out a boundary of his field. He simply mark out a boundary of his fields, and then he's whatever information he wants to provide, he provides. Like he says, I have sown wheat and this is the date, this variety. If he provides, it is good. If he does not provide, only he has to provide which crop he has sown. We should able to provide that it is the expected yield.
Yes.
On 1st of December, we should say this is expected yield based on long-term weather forecast, the situation. By 1st of February, we should say this is expected yield. By 1st March, this is the expected yield. By 30th March, this is the expected yield. So such a system, it needs a lot of cloud storage, programming, and computation. Now, other components we have fixed up, science and all, we have done it. But this need to be scaled up.
And another thing, like these soil health cards, in
Yeah.
your models, you require these fertilizers and soil health condition also.
Yeah.
Since these soil health cards are available, so the work which you are attempting now for at field level, so whether you are planning to use that also for that?
Soil health card, there are
Or-
2-3 issues. No, 2-3 issues. One is the way they have been prepared, there is a lot of uncertainty in them.
Yeah.
Second problem is the kind of inputs given, they are from farmers' point of view, not from crop simulation point of view. Like our simulation model needs
recommendation.
available nitrogen, depth wise.
Yes.
It needs what is the hydraulic conductivity.
Right.
It needs what is the textural class. So there may not be there in the. And our issue is that we always think we are not going to get that kind of information. So how to compensate for that? Whatever coming from satellites, and use satellites to estimate biophysical. Another work we are doing now to estimate also soil moisture and put it into the crop model. So soil moisture, so that irrigation, nothing we should ask from them. From soil moisture, we should able to simulate when he has irrigated and how much water stress was there or not. So that is another area.
And whether IoTs would be more helpful to you, like when you are having specific fields,
Yeah.
especially for moisture and all.
IoT would be great because they would able to provide much needed inputs to improve on our forecast. That would be great, of course.
More accurate and
more accurate. But again, IoT is
but
there.
Right now
There
they
is
are
a
nowhere.
cost, how they would data would be collected, how they would come to server and all that whole system. But I want that at least let us scale it out, because science we have done it, and start producing error with a factor of 2. It means I may be 100% in error. But once we put the system, we will start looking at where we had error, why we had error, and how to improve on that.
So right now, where you have selected the fields?
This we selected in Gurgaon, Rewari area. Because from IRA, it takes 70 kilometers to go measure and come back same day. So
like how frequently you have to measure their values?
Every 10 days.
Every 10 days.
That was when we developed this methodology.
Okay.
Now we don't need to go. Now, when we wanted to validate whether we estimate leaf area index, we estimate chlorophyll, we estimate phenology, we estimate how good or bad that is.
But that is required for other places also, if at all we have to.
If we want to validate our results.
Yes.
Yeah.
So we can help you out in at NEAP, we are having some field level studies where we have one in Bulandshahr, another one in Sonipat. They have Sonipat or Panipat, Dr. Subhashji? One of these. I think Sonipat only. Sonipat, na? Panipat. Achha. Okay. So another one in Panipat. And so there we will be selecting some farmers also for our socio-economic surveys.
So we can.
We can. I mean, train the farmers themselves or our field investigator who will be collecting the data. So he can help you out maybe in getting some data, and you can validate that data.
Actually, recently we have tied up with a private company, Myco.
Mm-hmm.
So they say they would be able to provide us field observed soil data and all for 10,000 farmers field. From
Okay.
Haryana, Punjab. But anyway, whatever they provide, that is their promise. I don't know what they will provide.
No,
But
our
if
will
we-
not be that much. We won't,
Maybe,
because
but
we take
we
very small
don't-
sample.
we don't need that much.
Um.
We want to validate the things in a different context, in a different environment. So that would be great. I think we can think of how to move.
So
in
here it will be wheat, sugarcane, basically in Bulandshahr, and in Haryana we are going to work for paddy and mustard.
Paddy and mustard. Okay.
So that is.
So actually, mustard and wheat are doable. Sugarcane crop simulation model is in fancy. It is not that good itself. But what I am saying that if we increase the number of farmers field and all, we can also compare with different machine learning techniques, developing empirical models, machine learning versus this technique comparisons. So that could also be done.
So
Anyway, we will discuss more
yeah,
in detail.
yeah. So far we have not done the sampling, but soon we are going to have that. So accordingly, maybe we can take.
But you would able to do kind of crop cutting experiment type?
No. Crop cutting experiment we won't be doing.
Yield to चाहिए finally.
नहीं तो, but that we can ask farmers, you know.
Farmer तो कुछ भी बोलते हैं.
No, but our results and all, they are based on that only. Like social scientists, they basically ask farmers how much he has sold, and since it will be continuous survey, it is not one day.
बताता है ना.
हाँ?
वो बोरियों में बताता है इतनी बोरियां हुई.
No, बोरियों में नहीं. We will take standard units.
Sir, namaskar.
Namaskar, Subhash ji.
Just a minute. Sir, actually, under this project, for as a sample, this crop cutting kind of this thing we will do ourselves. Actually, our people will go to the farmers field during harvesting period, and we will do some of the data. We actually will measure and calculate based on the reality.
40-50 फार्मर का मिल जाएगा क्या बुलंदशहर में?
हाँ, 50 का तो we are going to have 150 in fact. We will take from 3
जब आप
villages.
जाएंगे तो उन फार्मर्स फील्ड के जीपीएस से कोऑर्डिनेट्स भी ले लीजिएगा. आपके फोन में आजकल जीपीएस होता है.
वो that we will take all information, sir, let long and all through our GPS system.
Good.
And this even a house let long also will be taken where he is residing, and his field and his condition of
long-term project
well and all those things we are trying to take. Actually, it will be complete household survey.
Okay.
And we will develop a database. What Dr. Rajni is telling from these 3 states.
But what is the purpose for that project?
Our purpose is that that suppose government crop insurance scheme is there. We want to test that how far the impact
of various
real
schemes.
beneficiary. So some sample basis we can have the database. Already we have benchmark with us. For particular scheme purpose, we can again go to same people and we can compare it what has happened. So this is the main purpose for this.
Okay. क्रॉप इंश्योरेंस एक्चुअली एक बड़ा इंपॉर्टेंट एरिया बन रहा है क्रॉप यील्ड के लिए.
हाँ, yes sir. But the way with so much motivation, government initiated this scheme. It is not percolating with that speed. That is the thing.
So we are we are going to start it, and it is going to be long term, not for 1 year only and all.
Yeah.
So that is there, and we are going to have farmers of different categories, small, medium, large, like that. So maybe like we can attempt at least, if it is useful for your kind of experiments, it will be good.
Yeah.
This is a good idea, madam. What sir has explained, this kind of thing we should try to apply in the field level so that it can be verified, as well as we'll also get some expertise in that.
And the thing is, maybe we will get our field investigator trained from you according to your requirement. Basically,
Yes.
field में कैसे करना है. In IRI field, you can just let them know, or maybe one of us can know how the things are to be done, and accordingly we will tell you. So
Sir, sometimes we may together we may go and visit the farmers also. We
साहब
may
मैं
plan-
हर सीजन में 3 बार जाता हूँ,
Yes, sir.
क्योंकि आपने वो पिछले लेक्चर में भी देखा होगा कि हमें कंजर्वेशन एग्रीकल्चर, DSR,
Yes, sir.
वो सब करने भी हम जाते हैं. मैं तो बहुत सर्वे में जाता हूँ.
वो तो जरूरी है.
हाँ, उसके बिना होगा नहीं. फील्ड में अगर गए नहीं तो. अच्छा, ये क्वेश्चन आंसर में भी देयर इज ए क्वेश्चन.
Okay, I think it is.
It is from
Okay.
Agriculture Economics, AGC BPT. How to overcome the problem of unavailability of data for crop modeling?
वही डिस्कस कर रहे हैं. You come in network mode. So many of you are there. So one whoever is going to field, you can volunteer for that.
हाँ, लेकिन हमारी नहीं, इसके अंदर कुछ इम्प्रूवमेंट होने जा रही है. गवर्नमेंट के इनिशिएटिव भी हैं और कुछ एक हमारा माइंडसेट भी है कि हम लोग जैसे कुछ जैसे एजेंसीज हैं, आई डोंट वांट टू टेक, सपोज वो सॉइल मैप बना रहे हैं, सॉइल प्रॉपर्टीज के मैप बना रहे हैं, बड़े अच्छे रेजोल्यूशन पे बना रहे हैं, लेकिन वो पब्लिकली अवेलेबल नहीं करते हैं, डिजिटली अवेलेबल नहीं करते हैं कि एमिनेबल हों, उनको यूज किया जा सके. लेकिन अब एक गवर्नमेंट ऑफ इंडिया ने लास्ट ईयर स्कीम लॉन्च की है, स्वयंवत कुछ ऐसे स्कीम है जिसमें वो सारे हाउस होल्ड्स और खेत जो एग्रीकल्चर है उस सारे एरियाज को डिजिटाइज कर रहे हैं यूजिंग ड्रोन एंड ड्रोन बेस्ड सर्वेस. तो उनकी मार्किंग, उनकी ओनरशिप, उनकी सॉइल टाइप, क्या क्रॉप लगाते हैं, इस तरह का डेटाबेस. एक्चुअली यूएस में ये बड़ा आसान होता है काम करना, क्योंकि वहां पर हर साल किसने क्या क्रॉप लगाई है वो पूरा मैप पब्लिकली अवेलेबल होता है. आप पूरे यूएस का मेज कहाँ लगी है उस सीजन में वो आपको मिलता है. यहाँ तो हमें खुद जनरेट करना पड़ता है या फील्ड में जाना पड़ता है, फिर उसको डेटा लेना पड़ता है. तो कुछ हमारी प्रॉब्लम भी है कि हम लोग डेटा शेयर नहीं करते. कुछ गवर्नमेंट स्कीम ये ला रही है और हमारा बेसिक पर्पस यही है कि जो सिमुलेशन मॉडल को चाहिए, अगर वो ग्राउंड से नहीं मिल रहा तो हम उसको रिमोट सेंसिंग से लाएं. हम कोशिश ये भी कर रहे हैं कि रिमोट सेंसिंग से हम एक्चुअली टेम्परेचर, रेनफॉल, रेडिएशन ये भी एस्टिमेट होता है. तो वो जो मॉडल के इनपुट्स हैं उनको भी ये मॉडल को दिया जाए, इंस्टेड ऑफ हम वेदर स्टेशन के लिए वेट करेंगे कहीं वेदर स्टेशन से हमें डेटा मिलेगा. What is the impact of crop simulation modeling framework on the cost benefit analysis? This is a loaded question. I have never looked at cost benefit analysis. I am a physicist, not economist. तो हमने तो मेरे को उम्मीद ये है कि इसकी कॉस्ट तो मिनिमल है और बेनिफिट्स ज्यादा होंगे, स्पेशली इफ वी अप्लाई इट फॉर क्रॉप इंश्योरेंस. अगर हमारे फार्मर्स, अगर हमारा जैसे हमने दिखाया कि हमारा बेसिस रिस्क रिड्यूस हो जाए, हमारे फॉल्स ट्रिगर कम हो जाए, तो इसका मतलब हमारे जो इंश्योरेंस स्कीम की एप्लीकेबिलिटी काफी बढ़ जाएगी, उस पर कॉन्फिडेंस फार्मर्स का बढ़ जाएगा. सो दैट इज देयर इज अ गुड पोटेंशियल, a lot of more benefits would be there than the cost involved. और कॉस्ट सैटेलाइट डेटा तो आजकल नियरली फ्री है, बाकी कुछ कंप्यूटेशन, स्टोरेज और एनालिसिस की कॉस्ट है. More than 80% of our farmers are small and marginal and with low level of education. How to implement the modeling? I think modeling is not for the farmers. Modeling is for we scientists, and we have to generate applications which farmers can use by pressing few buttons. उनको बताए कि भैया इरिगेशन करनी है कि नहीं करनी है, फर्टिलाइजर डालना है कि नहीं डालना, आपकी यील्ड क्या इस बार एक्सपेक्ट करते हो. तो यू कैन एस्टिमेट, ही कैन एस्टिमेट व्हाट वुड बी हिज इनकम, मार्केट का प्राइस क्या चल रहा है. तो अगर मंडी प्राइसेस से आप लिंक कर देंगे तो आप उसका प्रॉफिट लॉस वो सब कैलकुलेट कर सकते हैं. फार्मर्स के लिए तो कहीं नहीं है कि हम फार्मर्स को मॉडलिंग करने की
मॉडलिंग सिखाएं.
ओके, थैंक यू.
So I think, and moreover, I would just like to add, when upscaling will be there, cost will automatically reduce. So this is also there. Now, when all takers were there, more people will be using it. Naturally, cost benefit will also improve.
Yeah.
So right now it is in development stages, especially such modeling.
हाँ अच्छा एक बात है आप देखिए हम लोग ऑलरेडी बहुत तरह के काम कर रहे हैं अब हम कॉस्ट बेनिफिट भी करने लगे तो हमारा एरिया नहीं है
नहीं नहीं, दे वांट टू टेल कि आप कॉस्ट बेनिफिट करिए हमारे साथ मिलके बिकॉज अब वो डीजी साहब भी कहते हैं ना हर चीज का इम्पैक्ट उसका वो देखिए कॉस्ट बेनिफिट टर्म्स में, तो इकोनॉमिस्ट तो उसी में ही देखते हैं इम्पैक्ट. And I think it was a good lecture and it generated lot of interest. Basically, some of the participants will be motivated to use such data for their research. So only thing is like how and where to get. Initially, they have to do this work in collaborative mode.
Yeah.
With the persons having knowledge of remote sensing at their respective place. I think all universities must be having some division of
agromet environment.
Yes.
While they do simulation modeling, and many of the universities have locally calibrated and validated these models for different crop in different regions. So
yes.
So those validated data or calibration data is really good because that will reduce our errors.
So one can use that. So the idea was to give a flavor of this newly emerging remote sensing data, which is now available in public domain freely. Earlier it was not available, but now it is getting available freely. So one can utilize that and solve the problem of unavailability of data. So yeah, so with that, we would like to thank you, Dr. Sehgal, for your presence and delivering a very beautiful and very thought-provoking lectures for the participant. It must have given them exposure of like complete full picture of this yield forecasting and yield estimation and the problems and challenges of using such data. So like I know you were hard pressed with time, but still you managed for this. So on behalf of participants as well as organizers, like I would like to thank you for your lecture. Thank you very much for being with us. Thank you.
Thank you. Thank you,
Yeah,
everyone.
thank-
Thank you
yeah.
for your patient hearing.
And no, it
I
was
could
really
generate
nice.
some interest.
Yes, yes, it was. So thanks a lot.